Hi, welcome back to another online lecture for Calculus 1. In this video, we're going to go through a topic called related rates. In your calculus course, this is your first time getting to solving word problems using calculus. So let me pull everything up. And we're good to go. So for this topic, there's going to be one central question through all these word problems. How does a rate of change in one quantity affect another? So we might have several quantities that all change in time. If one of them is changing, how does it affect the other or others? All right, let's think of an example maybe from your science courses to motivate this. Think back to maybe physics or chemistry with what was called an ideal gas. So we have P denoting the pressure, V denoting the volume, and T denoting the temperature of that gas. If we put that all together, we get the ideal gas law, PV equals nRT. Now we might ask, with P, V, and T all changing in time, how does one rate of change affect another? All right, we have several ways to think of derivatives. One way earlier in the course was we thought of derivatives as slopes of tangent lines. For this part of the course, we're going to think of derivatives as rates of change, instantaneous rates of change, if you recall. All right, and thinking of derivatives that way, if P and V change, so in other words, if P and V are changing in time with certain rates, what effect do they have on how the temperature T changes in time? All right, so we're going to keep in mind here that P, V, and T might all depend on something else. Most of these questions related rates, the something else is time. All right, so before we get into how related rates problems work or what they look like, let's go back to the starting place, which is implicit differentiation. So we have two examples here, which we covered earlier. The derivative of x squared with respect to x, which is 2x, but the derivative of y squared with respect to x is 2y times y prime. That y prime term is there because we assume y is a function of x. And we apply the chain rule. So if we put that to use to this equation, x squared plus y squared equals 1. This was our equation for the unit circle. We saw this in as an example in an earlier video. If we differentiate that equation implicitly with respect to x, we get this, 2x and then plus 2y times y prime equals 0. All right, now that equation was thought of under the assumption y is a function of x. Now for related rates problems, we're going to make a different assumption. Perhaps we have several variables, in this case x and y, and maybe both of them are functions of some other variable, usually time, t. Now if we encounter the same equation, x squared plus y squared equals 1, with this assumption, we apply implicit differentiation with respect to t, but now notice both x and y are functions of t. So when we differentiate both those terms, x squared and y squared, we're going to have to multiply respectively by x prime and then multiply by y prime. We're going to rewrite those primes, y prime and x prime, as dx over dt and dy over dt. So kind of this is what we'll see in related rates problems, and it all goes back to what we did with implicit differentiation. So keep that in mind. Earlier, only y was a function of x. Now, several variables, x and y in this case, might all be functions of something else, in this case, time. All right, so before we get into the true or classic word problems, where you have basically a big mess of a paragraph, you have to translate that into an equation, let's start with a basic example, one where the equation or formula is already given to us, just as a kind of an introductory example. So we have the example stated here. We have two quantities, x and y, and they're related by this equation, x plus y cubed equals x squared. Now, if we assume for this question that x is changing in time and y is changing in time, we can answer the following question. If x has a rate of change as 2, and that could be 2 units per time, whatever the units are. I'll leave it to your science courses to be more specific about the units, meters per second, joules per second, whatever. So we're just going to leave the units off. So if x has a rate of change as 2, what is the rate of change of y at the moment when x is 3 and y is 1? All right, so we're going to basically think of this as implicit differentiation, but with respect to time t. So if we kind of think of implicit differentiation, we'll differentiate both sides. In this case, we're differentiating with respect to t. We apply implicit differentiation, multiplying each derivative by either dx over dt, that's x prime, or dy over dt, y prime. Each quantity that changes in time, we have to multiply by that quantity's derivative following from the chain rule. All right, so just be careful. Notice you have x, y cubed, and x squared on the left and right side. And basically from there, we can translate this into the problem. If the rate of change of x, dx over dt, is 2, how then can we solve for what the value of dy over dt is? So at this point, we can basically plug everything in. We're going to plug in everything for dx over dt as 2, plugging in x as 3 and y as 1, and we can solve for the value of dy over dt. All right, if we do that algebraically first, we can subtract some terms over. And then in the last step there, to solve for dy over dt, we'll divide by 3y squared. So if you plug everything in, you should find that you get that dy over dt at the moment when x is 3 and y is 1 comes out to have the value 10/3. All right, so this is going to be kind of what we're aiming to get in a related rates problems. They get a little more difficult because we're going to have to come up with the equation for the example ourselves. Here in this example, that equation was given. In the standard related rates problems, you're going to have to construct that equation or formula yourself. All right, so before we get into the actual problems for our calculus course, there's kind of some standard steps like you might have had in solving algebra word problems. Now we're going to kind of apply them for our calculus course. All right, so it's kind of 5 steps. Most of the problems, when they give you all the information, a good first step is to draw a sketch. And that sketch will assist you with step 2, assigning variables to the quantities that can change. All right, once you have your sketch and variables, you can use those variables in step 3 to construct some sort of equation or formula. And once you have that equation or formula, that's at which you can now apply the tools of calculus. You can differentiate it and start solving for things once you have that equation, and then you can differentiate it. And then the last step is to solve the problem for the unknown rate of change. All right, so I'm going to want to copy these down so that way you don't have to refer back as we're getting to an example. All right, let's get to our first real example, example 2 here. All right, pause the video maybe to kind of understand the problem. Welcome back. This is a standard problem that pretty much every Calculus 1 student encounters, some sort of variation of this. It's a good introductory related rates problem. All right, and the basic setup is there's a ladder leaning against the wall, and then the bottom starts to slide away. And then we're interested in knowing how fast the top is sliding down the wall. All right, so let's think of step 1, drawing a sketch. So we have our kind of starting time sketch at t equals 0. So a 16-foot ladder leaning against the wall. Notice in the problem it tells you that the base starts off 5 feet from the wall. All right, now as time progresses, that base is going to slide away. We're told that the base is sliding away at a rate of 3 feet per second. Now, after 1 second, the ladder has traveled an additional 3 feet from that 5 feet that it was initially. So after 1 second, the base of the ladder is a total of 8 feet from the wall. All right, now keeping in mind here different times, we can see what quantities are changing. It's basically the distance from the base to the wall, and then from the top of the ladder to the floor. Since we have those two quantities changing, let's assign them with variables. We'll be boring. We'll call the horizontal distance x and the vertical distance y. All right, so now with those variables, we can translate to the problem into kind of some formal calculus language. With x as the horizontal distance, dx over dt is 3 feet per second. We're now interested in solving for what dy over dt is. All right, now in order to do this, we have to come up with some sort of equation or formula that relates the variables together, x and y. And notice your sketch, you kind of have a figure that looks like a right triangle. Now, x and y represent the side lengths of that triangle. So we might think we can get an equation applying the Pythagorean theorem. And if we do, we get the equation x squared plus y squared equals 16 squared. And as it turns out, this equation is going to work for this question. It relates our two variables that are changing together in a simple equation. Okay, now once we have our equation here, we're going to keep in mind that our variables x and y are both changing with time. So if we want to get some rates in there, derivatives, we're going to differentiate both sides with respect to t. The right side is going to be really simple. I have no idea what 16 squared is, but I do know when you differentiate 16 squared, that's a constant, that's going to differentiate to 0. So notice on the right-hand side, that derivative comes out to 0, and then we're applying implicit differentiation to both x squared and y squared, keeping in mind that they both change with time. So we have dx over dt and dy over dt, multiplying those two derivatives. And basically from here, we know what the value of dx over dt is. We're given that in the question, 3 feet per second. We now want to solve for what dy over dt is. Here we can do that in 2 steps. Subtract, and then divide by 2y. And if we do that, we get this expression for that derivative, dy over dt, negative x over y times dx over dt. Now to answer the question, we kind of have to plug in some values. In our sketch up there for t equals 1, the horizontal distance, the distance from the base of the ladder to the wall, is 8 feet. And what we have to figure out is then what is the y value at time equals 1. Notice in your end result down in the box there, we have x and y appearing in our answer for dy over dt. So we know x right now at time equals 1 is 8 feet. We're trying to solve for y. And if you apply the Pythagorean theorem, we can do that. And you should find that y comes out to be the square root of 192, which is approximately 13.86. So we now have our x value, which is 8. We have our y value at time equals 1. And dx over dt was given as 3. So if you plug all that information in, you should find that you get approximately negative 1.7 feet per second for your answer for dy over dt, the rate at which the top of the ladder slides down the wall. All right, now this is a standard example. This is probably like a moderate example in terms of difficulty. Let's take a look at maybe some other ones that get a little more complicated. Before we do that, there's probably some equations or formulas that would be good to review. Some equations that pop up pretty frequently for related rates problems. The one we used in example 1 is the Pythagorean theorem. And that happens a lot when you draw a sketch and you see some sort of right triangle in it. All right, a second set of equation or formulas to keep in mind are some basic trigonometric functions along with basic SOHCAHTOA. All right, and then a final set of related rates problems deal with volumes of different figures changing in time. And there's pretty much two examples that occur a lot. So a sphere of radius r, hopefully you are familiar with the volume formula. 4/3 pi r cubed. And then one a little maybe more unfamiliar, a circular cone of height h and base radius r. The volume here is 1/3 pi r squared h. So you might want to keep those in mind for certain volume problems within related rates questions. Just as a follow-up, why are there 4/3 and 1/3 in those volume formulas? Now, right now in Calc 1, I don't have a good answer, but as it turns out, the answer to that comes from Calc 2. So if you're curious where these formulas come from, why there's a 4/3 and 1/3 in the answer, take Calc 2, and you'll learn how to figure out those volume formulas. All right, so these are kind of the standard equations or formulas to keep in mind. There might be other more complicated related rates questions, but these three sets of equations and formulas should get you through most of what you'll encounter. All right, so here's a third example. This one deals with a volume problem of some sort. I'm going to pause the video and give this an attempt. We'll check back in a few minutes. All right, welcome back. For this question, we're told that the radius is changing for the sphere and the volume is changing correspondingly as well. So our starting place here is we need some sort of equation that relates the radius of a sphere to its volume. And fortunately, we have that already. That was one of our kind of formulas we reviewed in that previous part. We have our volume formula for a sphere, 4/3 pi r cubed. Now for this question, the radius is changing in time, which then means the volume is changing in time. So our variables here, v and r, both depend on time. All right, we're going to differentiate implicitly with respect to t. Keeping in mind for this problem, we're given dr over dt as 0.2 feet per second. And we now want to figure out what dv over dt is. So if we start with our equation and differentiate implicitly both sides with respect to t, we'll get to here. Notice we're thinking of 4/3 pi as a constant multiple. We can just bring that outside of the derivative there and just worry about differentiating r cubed with respect to t. All right, if you calculate those two derivatives, the left side should turn to just 1 times dv over dt, keeping in mind we're thinking of the 1 coming from the derivative of x, right? The derivative of x is 1. In this case, we say the derivative of v is 1, but times dv over dt. And on the right side, the derivative of r cubed is 3r squared times dr over dt. All right, from here, it's just a matter of solving for dv over dt. We can clean that up a little bit. Notice the factors of 3 cancel out. And we get this nice expression for the rate of change of volume with respect to time, 4 pi r squared times dr over dt. Now, before we kind of finish the problem, I always like to point out interesting mathematical results when they occur. And you might recall for a sphere, 4 pi r squared denotes the surface area. So in this rate of change of volume of a sphere, we have the surface area, 4 pi r squared, appearing. And that's an interesting result that leads to some higher level mathematics that you might encounter through the calc sequence as you get closer to courses, maybe Calc 5, maybe all the way up to Calc 27. All right, now if we come back to the problem, we basically just have to plug in our values here. We're given for the question dr over dt as 0.2 feet per second. And we want to find dv over dt at the moment when the radius r has the value 2. All right, if we plug everything in, we get, this comes out to 16 pi times 0.2. And if you work that out, you get an approximate decimal value of about 10.5 cubic feet per second. All right. That's basically end of example 3. We're going to take a look at one last final example, kind of a little more challenging than the rest of them. And here is our final example, example 4. So definitely pause the video, give the problem an attempt, and keep in mind your different formulas. Maybe with your sketch, you want to consider using the Pythagorean theorem. Maybe you want to consider some volume formulas. And maybe you want to consider some basic trigonometric ratios. So pause the video, give it an attempt, and we'll check in a few minutes. Good luck. Welcome back. Hopefully you're enjoying the Aurora Borealis behind me. All right, hopefully you kind of have some time to digest the problem and understand it. So if we start with our basic sketch, we have a rocket traveling up and a camera that's tracking that as it ascends. So just in case you're not sure there, I labeled them. We have our camera and rocket in case it wasn't obvious. Okay, so we have that horizontal distance given as 10 kilometers. Since the rocket is traveling up, that vertical height is going to change. And then due to the camera tracking the rocket, the angle is going to change as well. So if we assign variables here to the quantities that are changing, we'll denote maybe the height of the rocket by h. And then that angle, we'll use the usual variable from pre-calc. We can denote angles usually by theta. You can use any variables that you want, but use the kind of standard and obvious ones where possible. All right, so for this question, our variables that change in time are theta and h. All right, now for this question, before we click forward, the sketch does look like a right triangle, but notice we only have one given side length, that base length, the distance from the camera to the launching pad, 10 kilometers. The height is changing, and since the rocket is traveling up, the hypotenuse in that right triangle is changing, increasing as well. So we can't use the Pythagorean theorem here, even though we have a right triangle. There's 2 side lengths that are unknown. The Pythagorean theorem would only apply when you have 2 out of the 3, not 1 out of the 3 side lengths like we have here. All right, so with our variables, in the question, we can translate the rate of change of the angle, that's the 0.5 radians per minute, and then that is our given rate of change, d theta over dt. We now want to figure out and use that to solve for what dh over dt is. Since h denotes the height of the rocket, dh over dt is the rate of change of height, which is the rocket's velocity. So we're solving here for dh over dt with all these values. All right, now while the Pythagorean theorem won't work, this is a good example for us to keep in mind some basic trig ratios. And usually we can apply basic SOHCAHTOA to this. If you take a look at your side lengths in that sketch, the right triangle, relative to our angle theta, we have h, which is the opposite side, and 10, which represents the adjacent side. And if you think through basic SOHCAHTOA, opposite and adjacent, that sounds like it's related to tangent. So we'll use here tangent of theta equals h over 10. That's going to basically be our equation that relates theta and h together. All right, from here, we're going to imply or apply implicit differentiation. Notice leaving it as h over 10, you might be tempted to use the quotient rule. We're going to avoid that and think of dividing by 10 as multiplying by 1/10. This will be a little bit easier since we're now multiplying by a constant 1/10. All right, if we differentiate both sides with respect to t, we're going to apply implicit differentiation. The right side is considerably simpler. Notice on the left side, we have the derivative of tangent. Hopefully you recall the derivative of tangent is secant squared. But because theta depends on time, we get as our derivative on the left side secant squared of theta times d theta over dt. The right side, the 1/10 is a constant multiple, and h, that just differentiates to dh over dt, just like v did, differentiating to dv over dt in the previous example. All right, so from here, to finish the problem, all we have to do is solve for dh over dt. We can do that algebraically just by multiplying by 10. And we get here dh over dt comes out to 10 times secant squared of theta times d theta over dt. Now for these questions, we're always able to get a numerical value for the unknown rate of change. To make that a little bit easier, we might think of secant squared as 1 over cosine squared. Cosine works a little better with basic SOHCAHTOA. And to determine the value for cosine when the angle is pi over 3, notice that's given in the question. We're asked to find the rate of change of the height of the rocket at the moment when the angle is pi over 3 radians, which is 60 degrees. Hopefully recall either the unit circle or here, one of your basic special triangles. If you apply basic SOHCAHTOA to that, to the angle in the lower left corner, apply SOHCAHTOA, cosine of pi over 3 will be the adjacent side, 1, divided by the hypotenuse, 2. So you should find cosine of pi over 3 has the value 1/2. At this point, we can plug everything in. We have d theta over dt given as 0.5 radians per minute. And in that denominator, cosine squared, cosine of pi over 3 is 1/2. Cosine squared of pi over 3, that is 1/2 squared. And if you plug all that in and simplify it, you should find you get as your answer 20. And then the units, just to be consistent with your science courses, here, the distance is measured in kilometers and the time in minutes. So we get the rate of change for height of the rocket's velocity, as 20 kilometers per minute. All right, that concludes our online lecture for related rates. Definitely go through this again. Pause the video at various spots. And we'll be back for more through our online version of Calculus 1.